That'll get you that proton transfer step will get you to here.
That's why they send this shit out.
All right. And then once you're here, again, this is going to follow pathway similar to SN1, right? Loss of leaving group is going to be your rate determining step. All right, so the water leaves. It leaves you with a secondary carbocation, which is here. And then you got these two methyl groups up here, right? And so if you look at the product, which is here, right? That looks nothing like that carbocation intermediate. Right? It looks nothing like the intermediate. So what happens with the intermediate is a methyl shift. Again, you got a secondary carbocation right here, and you can turn it into a tertiary carbocation if you do a methyl shift, which is a type of rearrangement. Right, so through a methyl shift, you can turn that secondary into a tertiary carbocation. So, and it's a very simple rearrangement. You take, and this is actually a CH3 group, right? The end of every line is a CH3. So you're just going to take that and move it to here, right? The whole group, the carbon atom plus both electrons. And what that's going to open up, right down here. It's just going to generate a new carbocation. The plus charge here, right? And now from that, that's where your elimination is going to take place because there is a hydrogen here on this carbon. It's just not shown, right? It's here too, and here. Right, so now you can do your elimination. And I always like to use the conjugate base of the acid to do the elimination. Right, so this is coming here. And then boom, like that, put the double bond in, and that'll get you to your product. Just gonna write it out. Right. So that's with the E1. I wanted to make those two situations kind of known to you. That sometimes with the E1 you can see you'll get some rearrangement if you have a chance to make a more stable carbocation. All right. Any questions about that? How many of you actually worked on this over the weekend? Anybody?
I did.
Yes.
Okay. Does this confirm what you did or did you do something different?
No, I did that.
Okay. All right, good. Good. All right. Now we've covered substitution and elimination in pretty good detail. We know about the rate laws. We know about the things that speed the reaction up. We know about the different leaving groups, how to tell which leaving group is better based on the pKa of the conjugate acid. We know the mechanisms, the arrows, we what else did we study? The different types of substitution mechanisms, SN2, SN1, and the different characteristics like inversion or Rasmusation. If you have a stereo center present, we learned about Zaitsel's rule with elimination. We also learned about elimination and the characteristics of that, the geometric constraints of having to be anti-periplanar, leaving group, and the alpha hydrogen being anti-periplanar. We learned that for E1, there's no geometric constraint because you go through a carbocation intermediate. That the E2 prefers tertiary substrates. That Zaitsel's rule governs the product distribution, and the major product is always the more substituted alkene. So we learned quite a bit under those two topics. So we're going to move on to another topic, and we're going to look at excuse me, conjugation. We're going to start talking about that today. So let me pull these handouts up and import them into Notability, and then we're going to just jump right in. And hopefully you had a chance to watch that conjugation video, because we're going to go over that again a little bit today, and then we're going to talk about two reactions that conjugated dienes do. They do a lot more reactions, but we're only going to focus on two. And let me pull that in too. Never mind. I can combine them later. All right. So let me just give you an overview of what we're going to do. So we're going to discuss the orbital or hold up, that's not good. We're going to discuss the, let me do it this way, MO theory as it relates to conjugated systems. And then we're going to discuss two reactions, cycloaddition and then conjugate addition. Of HX to conjugated diene. So we're going to talk about those two reactions. But first, we got to talk about just the concept of conjugation and why it's important. And it's actually a very important concept. So the basic definition of conjugation is when you have alternating pi and sigma bonds, right? So if you look at this example right here, you can see that you have a pi bond, and then you have a sigma bond here, and then you have another pi bond. So it's basically two pi bonds separated by one sigma bond. But conjugation can be extended past that, right? You can have a conjugated system that might have 10 pi bonds in it, right? So you can have something like this, right? And so you have the number of pi bonds that are a part of that system. It just depends on what type of system it is, right? So you can have extended conjugation, but as a layman definition is alternating. The definition of conjugation is alternating pi and sigma bonds. Right, I say pi and sigma because it's not limited to double bonds, right? You can also have a conjugated system that includes a triple bond, like the system that's shown here. And again, They have to be alternating. And the reason for that is because of the orbitals overlap. So what makes a system conjugated is when the p orbitals are able to overlap with one another. So you probably should have seen that in the video. So now let's just look at identifying conjugation first, and then after that we're going to look at the molecular orbital considerations for conjugation and what they actually point to. Right, so you can have a system like this, right, which is not conjugated because you have a pi bond and then you have two sigma bonds here separating it from the next pi bond. And what that does, if you think about what a pi bond is, it's actually two carbons that overlap p orbitals that are unhybridized, right? And so if you wanted to conjugate that or overlap it with another pi system, the pi system would have to be right next door. All right, so the next pi bond will have to be on two carbons here, right? So this would be your pi bond, this would be your sigma bond, and then this would be pi, right? Because the whole idea behind conjugation is that you're creating a larger molecular orbital from individual atomic orbitals. All right, so we'll talk more about that in a second. But if there's more than one sigma bond between the two pi bonds, then the system is not conjugated, right? And there's also a further definition, which is that something can be what we call fully conjugated. Right, and what that means is that there is a p orbital on every carbon. Right, and this definition is going to matter when we get to aromatics, right? Because one of the criteria for aromaticity is that the system be fully conjugated. All right, so let's look at some of these examples down here and see if we can just pick out uh, what's conjugated and what's not conjugated. All right, so that first system, the benzene ring here, what do you think? Is it conjugated or is it not?
Conjugated.
It is, right? Because you have a pi bond separated by a sigma bond, then you have another pi bond here. Is it fully conjugated?
Yes.
It is, right? You can put in, the way you test that is that you can put in the p orbitals here on each carbon, and what you'll see is that there's a p orbital on every carbon in that system. So this is an example of a system that is fully conjugated. All right. What about the next one? Is
Conjugated.
It is
But
conjugated,
not fully.
but it's not fully conjugated. Good. All right. There's a p orbital on these 4 carbons, so it is conjugated, but it's not fully conjugated. Right. What about the naphthalene system, the fused ring system here? What do you think? I mean, obviously there's conjugation, right? You can look, if you just look at the double bonds and the single bonds, you can see that they're alternating, right? You have a double, single, double, single, double. And then if you look at the rest of the system, you'll see that this is also a fully conjugated system. All right. Again, if you put the p orbitals on each carbon, you can see that. All right. What about here?
Not conjugated.
It's not, right? You need at least 2 double bonds to be present in order for a system to be able to have conjugation or display conjugation. So that's not conjugated. And here. So that's a lag between my iPad and my screen. Sorry about that. What about here? What's the problem here?
It's not conjugated.
Right.
There's
You,
two
Two
single
bonds next to each other.
so you can see there's a sigma bond here and here, and what that does is it keeps these 2 orbitals right here from overlapping. It'll come up. It keeps those 2 middle p orbitals from overlapping. So that breaks up the conjugation, right? And you can see right here on the last example, that's also conjugated, but it's just not fully conjugated. You can put the p orbitals in, and you can see that there's alternating double and single or pi and sigma bonds in that system. Right? So when you have a conjugated system, right? I think it should have been in the video, but when you have a conjugated system, what conjugation is a concept of is what we call molecular orbital theory. Right. And so what molecular orbital theory is similar to hybridization, but it's not the same. For the longest time, I struggled with trying to differentiate between the two, but they're not the same. MO theory it basically says that you can add atomic orbitals and when you add those atomic orbitals, you generate what's called molecular orbitals. All right, so you add atomic orbitals to generate molecular orbitals. So what it does is it allows us to understand the reactivity of really complex molecules and complex pi systems, right? So if you look at that top example, all right, how many p orbitals are present there?
4.
4, right? You got a p orbital here. Let's zoom in a little bit. Come on. You have a p orbital here, 1 here, and 1 here. It's coming. It's just lagging, right? So in this case, you have 4 p atomic orbitals. So what molecular orbital theory predicts is that you can generate from those 4 p atomic orbitals, you should generate 4 molecular orbitals. Right? So 4 p atomic orbitals should give you 4 molecular orbitals. The way I like to think about it is that there are 4 different ways that those p orbitals can combine, right? And the way you illustrate that, you should have seen this also in the video, is you illustrate it using what's called a molecular orbital diagram. Right, so the way you illustrate that is a MO diagram, and the MO diagram is basically based on the particle wave duality of an electron, right? So if you consider electrons as particles or as waves, then they have characteristics of both. And so when you think about an electron as a wave, what that means is that it's going to behave like a wave, right? And so if we just took like a simple 2-pi system, it's not conjugated. You can't conjugate unless you have at least 2 pi bonds. But if you take a 2-pi system like ethylene, right, the p orbitals on ethylene are here. So I got 2 atomic p orbitals. So I should be able to generate 2 molecular orbitals. So I would just draw them like so, right here.
Excuse me, sir.
Go ahead.
I just want to make sure I'm clarified. So you're saying that you said that the number of p orbitals gives you the number of molecular orbitals, or that the number
Yeah.
of p orbitals, with that amount you can get up to that many molecular orbitals?
No, it's got to be equal. It's got to be equal.
Okay, it will be equal. Okay.
Yeah. So if you got 4 p orbitals, they're going to generate 4 different molecular orbitals. And you'll notice, and so this is a molecular orbital, right? It's the 2 p orbitals are combined. Then I got a second molecular orbital here, because those p orbitals, if I got 2 p orbitals, they can combine in 2 different ways. So that's why you see 2 different molecular orbitals.
Mm-hmm.
Does that make sense?
Thank you. Yes, sir.
All right. So now here are my molecular orbitals, and then again, I'm treating this like a wave. And so if I think about it as a wave, then there's some other things I have to take into consideration, like the energy of the wave, which is going to increase going in this direction. And I have to think about the behavior of the wave. So in the lowest energy level, or the ground state, right, that wave should never pass through 0. Right. And then as I increase in energy, I'm also going to increase the frequency of the wave. So when I get to the next energy level, the wave is going to pass through 0 one time. Right. So this is the first harmonic. If you took physics, probably heard this before. And this is the second harmonic. All right. I'm just going to abbreviate it instead of trying to cram that in there. So first harmonic, second harmonic, right? And then the other thing you have to take into consideration, which matters, is the sign of the orbital, right? How many of you remember from Organic 1 that if you have a p orbital, right, just a generic p orbital, how many of you remember what that orbital represents? Anybody? What does an orbital represent?
A space where electrons reside.
So the path, it's an equation of the path that that a proposed path that an electron travels around the nucleus of an atom, right?
Mm-hmm.
It's not the equation, it's the graph of the equation. Come on, Russell. So it's the graph of an equation of the path of an electron. It's coming up. I don't know why there's this lag. My birthday's coming up. I think I'm gonna buy myself a new computer for my birthday. A real fancy one. Come on. Hold up. Let me do something right quick. I'm gonna reshare my screen because this is really frustrating. All right. So that p orbital is a graph of the equation of the path of an electron, right? So if you remember that there's an organic one, there's a node in the middle, right, where the wave or the graph passes through zero, and then no electrons can be there. Right, but electrons can be in the top part of the lobe or the bottom part, and then the lobes have, since it's an equation, they have a sign, right? So they can be positive or negative. So we're going to say that this part is positive and this part is negative. Or we could say that one part of that is shaded and one part is unshaded, right? Either way you want to express it. But the shaded and unshaded just means that there's a sign difference. But shaded doesn't necessarily mean positive. Unshaded doesn't necessarily mean negative. It just depends, right? That's arbitrary. All right. So we can say that the shaded means that the sign of the orbital changes. Are y'all following that?
Yes.
Yeah. So it's just a way to indicate that each lobe has a different sign in that graph, right? So if we go back up here, we can look at the bottom, the first harmonic, and we'll say that these are both shaded because since the wave never passes through zero, then the sign of the equation should never change. Does that make sense? So the wave is also corresponding to that molecular orbital. So since the sign of the wave doesn't change because it never passes through zero, then the signs of the orbitals won't change either. All right. And then if you look at the top, what do you think? The wave passed through zero one time. So that means that if this orbital starts out as shaded, then the sign of the wave changes, which means that the sign of the orbital should also change. Yes or no?
Yes.
All right. Any questions about that? So this is an example of a 2-pi system, right? Where you have 2-pi electrons. Let me put the electrons in too. So we can put the electrons here. All right, so you got 2 electrons, and you always fill up the low energy orbitals before you move up. That's just following Hund's rule, right? Where you fill up all your degenerate orbitals before you move to the next energy level. All right. So with that being said, this molecular orbital diagram will tell me how this system is going to react, right? If it's acting as a nucleophile, it's going to react through the orbital where the electrons are. I'll write that down here. If it's a nucleophile, this is the orbital that is going to react through where those electrons are. And then if it's acting as an electrophile, then it's going to react through the empty orbital, because nucleophiles donate electrons and electrophiles accept electrons. Is that right? Based on what you learned in Organic 1, a nucleophile is an electron donor and an electrophile is an electron acceptor. So this diagram is going to tell me how this system will react depending on if it's reacting as a nucleophile or if it's reacting as an electrophile. All right, is that okay? Anybody got any questions about that? All right. All right, let's look at the 4-pi system then. And then we're going to do the diagram for that as well. So if we have a 4-pi system, what that means is that there are 4 pi electrons, right? So a 4-pi system, one way to express it would be to show just a simple conjugated diene. Right? And each one of these alkenes in the diene is going to have 2 p orbitals. Right? But because it's conjugated, the 2 p orbitals in the middle are going to overlap, and they're going to actually cause this to go from just being 2 separate pi systems to one big pi system. That's why we call it a 4-pi system. Right? So these 2 orbitals in the middle are going to overlap. And when they do that, they actually shrink down or compress that sigma bond between those two pi systems. So instead of it being, again, 4 separate p orbitals, now you got 4 p orbitals that are all able to overlap and share electrons. All right. So with the 4 pi system, right, how many p orbitals am I looking at again?
4.
So 4 atomic orbitals. That means I should be able to generate 4 molecular orbitals. All right. And again, it's the same concept from before, right? So each molecular orbital is going to contain 4 p orbitals. The only difference is going to be how the lobes are shaded and where the electrons are, right? So if I generate 4 p or 4 molecular orbitals, one of those molecular orbitals is going to look like that, right? With 4 p orbitals in it. Let me see if I can cheat right quick. I think I can. Maybe not. Never mind. I'll just draw them out. I was trying to be lazy. So that's one. Then we'll have another one that looks identical to that, right? Each one of these molecular orbitals is going to contain 4 p orbitals. And again, each one of the molecular orbitals is going to follow, it's going to have the characteristics of a wave, right? That's how you generate your molecular orbitals, because you're looking at electrons as having particle and wave properties, right? So come on, man. This thing is really lagging. All right, I'm gonna try it again. Boy. Come on, stop acting goofy. All right. So these are what the 4 molecular orbitals will look like. Now we have to think about the other stuff, right? The shading, the first harmonic, second harmonic, third and fourth harmonic, so on and so forth, right? But before you even worry about the shading, just think about the wave, right? Every one of these orbitals is going to follow the characteristics of the wave. So this is the way here, the wave never passes through 0, And the wave has the same characteristics no matter if you have 100 orbitals. It's going to be zero time, no times passing through zero. Then it'll pass through zero one time or have one node. And then it'll pass through twice. Then it'll pass through 3 times, like so, right? So if you remember the wave pattern, then the shading and all that stuff is trivial, right? So in the first harmonic, where it never passes through zero, I'm just gonna, right? The sign of the equation never changes. And so each orbital is gonna have the same sign, right? All of them will be either, the top half will be all shaded or all unshaded. It depends on how you want to do that. I like to just keep it shaded because it makes it easier when you move up to the higher energy levels. All right. What about the next? What would you do for the next set of orbitals?
Shade the first two
So the first two will be
at
shaded.
the top,
Okay.
and then the second two shade them at the bottom.
Okay. All right. And then, what about the third harmonic? I'm sorry, the second harmonic. Third harmonic, my bad. What would you do with the two in the middle?
Shade the bottom half.
On both of them?
Mm-hmm.
All right. And then it'll switch again here. Right. And this matters when you talk about reactivity, right? Again, those shaded and unshaded lobes, when these dienes react with other species, that's how they react, by overlapping orbitals with something else that it's reacting with. All right. So the molecular orbital that you choose as your reactive molecular orbital matters, right? And it matters about whether it's in the ground state or in the excited state, which we'll talk about later. So yeah, so let's look at, what about the top? It should just be alternating. Is that right?
Mm-hmm.
Yes.
All right. So that's the diagram for a 4-pi system. And then since it's 4-pi, that means there's 4 electrons. So we need to put the electrons in. All right. So I'm just gonna draw here. All right, each one of these can hold a pair of electrons. But since you only have 4 electrons, you got to fill up the low level orbitals first, right? So here and then here. So this top orbital right here, this is where it would react from if it was acting as a nucleophile, right? This is what you call the HOMO. And that's a acronym for highest occupied molecular orbital, all right? And then the orbital above it that's empty, we call that orbital the LUMO. Right, call that one the LUMO, lowest unoccupied molecular orbital. So anytime a pi system reacts, it's going to react either through its HOMO or through its LUMO, right? If it's acting as a nucleophile, it's going to react through the HOMO. If it's acting as an electrophile, it's going to react through the LUMO. It just depends on what what type of reaction is taking place. All right, so for a 4-pi conjugated system, this is the molecular orbital diagram for that. All right. Obviously, with conjugation, you can have as many pi bonds as you want, right? You can have a 10 pi system or 8 pi, 9 pi. It doesn't matter. The point is that it's all going to be based on the wave, right? And it's going to be based on again, the characteristics of a wave. So it doesn't matter how many p orbitals you have, right? The first harmonic, the wave is not going to pass through 0. And the second harmonic, it'll pass through once. And then when it passes through 0, it has to be symmetrical. So if you have 6 p orbitals, for instance, it'll fall right between the first 3 and the last 3 in the second harmonic, so on and so forth. So it cuts symmetrically, but also it doesn't matter how many orbitals you have, it's going to follow the same pattern. It's going to pass through 0 once in the second harmonic, twice in the third harmonic, 0 times in the first harmonic, so on and so forth. Like that. All right. Any questions about anything so far?
No, sir.
All right. So that's the basic MO theory behind these conjugated systems. And so what we're going to do, because the test is going to be Friday, I'm only going to cover one of the reactions. We're only going to do cycloaddition. And then we'll come back and do the conjugate addition later, because I don't want to try to do both and then cram it all in. I don't want to do that. I think that'd be a disservice to you actually trying to learn it. So I want to start out talking about cycloaddition, and then we'll come back to the conjugate addition. All right. So I'm gonna put this here. And there's a lot of different cycloaddition reactions. You can have a 2 + 2, you can have a 3 + 2, but we're going to focus on 4 + 2 cycloaddition. Right, so it's going to be a 4 pi system reacting with a 2 pi system. I have to restart this computer. All right, so a 4 pi reacting with a 2 pi. It's actually a named reaction. It's called a Diels-Alder cycloaddition. Right, and it's not. It looks complicated, but we're going to break it down to the point where you understand exactly what's going on. Right, and so let me show you the fundamental reaction. Right, so you have a 4 pi system, which is a conjugated diene. So we'll call that 4 pi system the diene. And then you're going to react that with a 2 pi system. So this is 4 pi. This is 2 pi. And this is what we call the dienophile, or lover of dienes, right? So the phile comes from the Greek word, one of the Greek words for love, philos, where we get, it's like brotherly love, like the city of Philadelphia. That's where that name comes from. All right. So you have a 4 pi system, you have a 2 pi system, and then when you heat them up together, right, what you get out of a 4 + 2 cycloaddition always is a 6-member cyclohexene, right? A 6-member ring that contains a double bond. So I'm gonna write that. I'm gonna have to zoom so I can fit it. right? So that is the outcome. It's a 6-member cyclohexane ring. Based on those two, the diene and the dienophile reacting together. All right, and we're gonna talk about the mechanism and all that stuff. One of the things that this reaction, one of the characteristics is that the diene is going to react through its HOMO, and the dienophile is going to react through its LUMO. Come on. I'm gonna pause. I'm just gonna stop right there because this thing keeps freezing up. But I think I only sent you the video dealing with conjugation and molecular orbitals. So what I'll do is I'll send you a Deals Order video after class for Wednesday, and then we'll pick this back up on Wednesday. And we'll talk about the transition state, HOMO-LUMO overlap, and we'll work through some examples. All right, any questions about anything before we sign off? No questions. All right. So yeah, let me stop recording, and then I'm gonna end the meeting, and then I'll upload everything to where it's supposed to go. I'll upload the notes to Blackboard and upload the video to YouTube, and then we'll see y'all back again on Wednesday.
Thank you, sir. See you Wednesday.
Okay. Thank you. Y'all have a good day.